special solitons to mold and root random lazy liquid crystals. The topic is concerned with solitons, which are self-guided light beams in a medium which is nematic liquid crystals. And the idea is to use a passive nonlinear response to make a waveguide, control the light guided in such a waveguide, and with this in mind, also control random lasing in doped liquid crystals. So combine passive and active nonlinear optics into some nematic-based photonics. So basically, let me remind you what I mean by a spatial soliton. When you have light propagating in a linear medium on the left, and you have a finite beam, the beam will diffract, so the phase front will curve forward, and they become convex, and thereby you have linear diffraction. If you are in a nonlinear medium with a curve-like nonlinear response whereby the index is a linear function of the intensity of light point by point, the same type of beam will induce a variation in index according to this law, and such a variation in index is if the coefficient n sub 2 is positive, is a self-focusing response, and will induce a phase front curvature which is opposite in sign to the previous one. So the beam will tend to converge and focus. So the self-linear diffraction on the left and the self-focusing convergence and focusing on the right could compensate at a certain energy level or power level. So if you have an intense enough light beam propagating in a nonlinear medium with such a nonlinear response, your diffraction will reduce. And so as you see in this animation, from linear diffraction, as you increase the intensity, a Gaussian beam will tend to diffract less. And if you increase the intensity even more, it will diffract even less until the two effects will balance. And the result is a self-guided beam, because diffraction has been compensated by self-focusing. And so there is no longer diffraction, and the beam will propagate with a constant intensity distribution, velocity, and shape. This is called a spatial soliton. And the spatial soliton is not only a self-guided solution of the nonlinear Schrödinger equation in this case, but it's also a waveguide, because you can imagine that this change in index described by this Kerr law with a linear dependence on intensity will induce an increase in index along the shape of the beam in the Characterization dimension. And so this will induce a waveguide, a graded index waveguide. So at the same time we are self-localizing the light beam, we are making a waveguide, an index waveguide, and so the guided beam is actually the normal mode, which is guided by the self-induced waveguide. So this self-sustaining mechanism is called a spatial soliton, and it's really important because it's the only solution in nature by which light can induce its own waveguide and thereby beat diffraction in propagation. Now, for the, let's see, okay, the medium we chose is nematic liquid crystals, which is known to you, particularly in the nematic phase in which we have orientational order and no positional order. Now, this is a uniaxial medium by which the refractive index along the extraordinary polarization is higher than the refractive index in the ordinary polarization. So if we use an oriented cell in which all the molecules are oriented along the same direction, we have a positive uniaxial in a liquid state. So working in this type of medium, we can easily imagine that the application of an electric field, which could be a static electric field or an AC electric field, or the electric field of a light beam, as indicated by the green arrow, will induce a dipole in the molecules. And the molecules are elongated and anisotropic. So this dipole will react to the electric field, and by way of this torque indicated by gamma here, the reaction of dipoles with the electric field will tend to move the molecules from their initial position at an angle theta to a new position which is with a larger angle theta. So the molecules will rotate to minimize the energy of the system, and thereby the orientation of the molecules in the system will induce a variation in the orientation of the optic axis of this uniaxial medium. But a variation in the angle theta, a variation of the optic axis orientation with respect to the E field, will also induce a change in index of diffraction. Because as you know, for the extraordinary polarization in a uniaxial, the refractive index for the extraordinary polarization, which is a field polarized in the plane of the optic axis and the propagation wave vector, will be a function of theta. So by increasing the angle theta between the molecular director and the wave vector, I also increase the refractive index. This increase in the refractive index mimics the Kerr law I indicated before. And so this is an electromechanical mechanism by which I can increase the refractive index and induce a self-focusing response, which is what I need to make a spatial soliton. So in a suitable cell oriented like this, if I launch a linear beam, the linear beam will diffract as indicated in this sketch. If I make a photograph in a sample at the bottom, this is a real cell at 514 nanometers, you see the beam will diffract. If I look from the top, I see the beam diffracting as it propagates for a millimeter or so. And at the output, of course, I will see diffraction. If the cell is long enough, diffraction, losses, and scattering will combine, and thereby I will see no transverse shape of this propagating beam upon diffraction. However, if I increase the electric field in the extraordinary polarization, as indicated in this sketch, I can induce the torque I indicated before by inducing dipoles in the molecules, and this reorientation will tend to, let's see if it works, will tend to move the molecules along the propagation of the beam. This rotation of the molecules will increase the angle theta. This increase in theta will increase the refractive index. And this increase in refractive index will eventually form a waveguide, as I described before, by which the beam will, let me see, okay, will self-confine into a soliton. And so at the output, instead of diffraction, I will get a self-localized beam, which is self-guided by the waveguide induced by this nonlinear response. And this spatial soliton is characterized by a beam spot which is of the same size of the input, as indicated here. But the waveguide itself is much wider, as indicated by the black curve on the left, because the response of the medium is the response of a fluid. And so the molecules not only rotate where the field is present, but also rotate nearby because of elastic forces. And so the result in a simple experiment with 2 milliwatts power is a soliton as you see on the bottom left. So it's now a self-guided beam which has no diffraction because it's now the normal mode of a waveguide induced by rotating the molecules along the intensity profile of the beam itself. So this is a photograph of a 2 milliwatt spatial soliton in a nematic liquid crystal cell undoped. And at the output, of course, you see a transverse profile which resembles the the fundamental mode of a guided signal. So these objects in nematic liquid crystals we called nematicons. And nematicons have been studied for about 20 years because there is, you can imagine, a lot of physics involved and a lot of interesting aspects to be studied. But we wanted to move from the physics of nematicons to the photonics of nematicons. And we decided to combine this nonlinear effect with an active nonlinear effect, which is random lasing. The same type of materials, with the proper dopants, you can induce random lasing in liquid crystals. I don't know how many of you are familiar with random lasing. If we compare a standard laser on the left top with a cavity and an active medium with a random laser is a cavityless system in which you can get lasing because, of course, you have gain, light amplification, because some dopants are able to produce amplification of emitted photons. You have spontaneous and eventually stimulated emission, but the cavity is given by random scattering. So the scattering available in such a random medium provides feedback, optical feedback. So the stimulated, the spontaneously emitted photons can actually make cycles and come back onto their own path, making a resonance. And this resonance, without an external cavity, can induce random lasing. Of course, resonance induced by random scatters will have a broad spectrum and will have a poor coherence. This was demonstrated a while ago, and here is the reference to an early paper in 1994 by Lawandi. So it was understood a while ago, and it was later demonstrated also in nematic liquid crystals upon suitable doping. In nematic liquid crystals, here is a paper by Strangi and co-workers. In nematic liquid crystals, it was enough to add some dopants to provide absorption of a pump light, induce amplification in the medium, and by the natural scattering present in the nematic liquid crystal medium, they could observe random lasing using some pyromethane dye in standard nematic E7. And here you see the response of this random laser, in which they use a neodymium YAG laser doubled at 532 nanometers, and they observed the typical spectrum of a laser with a very sharp line, as you see in this graph on the top right. So going from standard fluorescence below threshold to lasing above threshold with a very narrow laser line, very sharp intensity, and also the emission of a mode indivisible, in fact in the orange light, but at a random direction with a random transverse profile. And this randomness is intrinsic to the random lasing process, because not having an external cavity, you cannot control the specific resonance, you cannot control the coherence, and you cannot control the direction of emission of this emitted light. And so a random laser is characterized by the lack of an external cavity, low coherence, a poor spatial profile, a random direction of emission, and of course a spectrum which is not very sharp as compared to a standard laser. What you see on this graph here is a comparison between different types of random lasers using nematics in red, using some dye medium with scatters provided by zinc oxide powders, and in black cholesteric. You see that the random laser in nematic liquid crystal is actually pretty good given by this red line. You can see the elbow and the starting of the lasing action with a large amplification upon increase of pump energy above a threshold. So this is a characteristic of a laser, and in particular of a random laser. Now, because all this happened in nematic liquid crystals, and because all these bad features of a random laser are not useful for applications, we decided to combine the special solitons with random lasing in the same nematic liquid crystals. And the purpose of this would be to provide an environment to the random lasing action in such that we could improve the directionality of the laser, the coherence of the laser, the transverse shape of the beam, and control the threshold of the lasing action. So we thought of putting in synergy passive nonlinear optics due to reorientation in nematic liquid crystals, and active nonlinear optics due to this stimulated emission in the presence of a suitable dye and external pumping to make a random laser. For the experiments, we prepared a standard cell with nematic liquid crystals oriented at a certain angle in the principal plane for the extraordinary polarization. And looking at the top of the cell, we had two beams at the input. One beam is indicated by red and is a near-infrared beam inducing the special soliton which I described at the beginning. This extraordinary polarization will make a soliton, a nematicon, a self-guided beam, a self-induced waveguide, able to guide extraordinary light produced by the lasing action. And then also we need a pump, indicated by the green arrow. The pump is necessary to provide amplification through absorption in the dye molecules, because we need a means to provide gain to obtain lasing action. We used an ordinary polarized pump in green The ordinary pump is not guided by the soliton, because the ordinary polarization is not subject to reorientation, and so it diffracts in propagation in the cell, as indicated by the green cone. The red light is near-infrared made as soliton, or a nematicon, and you see the nematicon is not diffracting, and it's actually propagating at an angle which is the walk-off angle. We'll come back to walk-off in a few slides. N indicates the position in angle of the molecular director. So this is our planar cell, able to provide optical gain and nonlinear reorientation, so able to sustain both a soliton, passive linear optics, and optical gain through pumping with a pump, which is indicated by green, and eventually random lasing above a threshold. And so we launched both beams in the cell, moving the molecules in the plane by means of the near-infrared beam to make a soliton. And then for various continuous powers of the soliton beam, and milliwatt power levels, we could study the pumping threshold of the green in order to induce random lasing. The pump was a doubled neodymium YAG at about a millijoule energy level. And here you see the pump energy per pulse indicated in microjoules. And here you see the peak intensity at the output of the random lasing system for various CW milliwatt power in the near-infrared beam. So we have two parameters. We have the pump energy to pump the system, and we have the control light in the near-infrared to form a soliton and guide the laser emission. And as you can tell, at 0 milliwatt, of course, we have no soliton, so we have regular diffraction, and we get a laser with a certain threshold and a certain amplification, indicated by the black dots. But as we increase the power in the near-infrared, we form a waveguide, a light-induced waveguide. The light-induced waveguide is able to guide the emitter light in this ordinary polarization. The emitter light is confined in a limited volume given by this solitary waveguide, and thereby the interaction between spontaneous emission and pumping and amplification is improved, and so the laser, upon making a waveguide, gets a higher amplification with a higher slope of the laser emission after the threshold. So we go from black to blue to green to red by increasing the soliton power by a few milliwatts. So we are able to control the emission and improve the amplification of the random laser by increasing the power from 0 milliwatt to 6 milliwatts in a near-infrared beam which forms an optically induced waveguide. So this is a demonstration that guiding the emitted light will increase the efficiency of the random laser in a limited volume in propagation in this 2 millimeter long sample, planar sample. So nematicons tend to enhance random lasing. You can tell that the efficiency is getting higher and higher here. And then if we look at the other characteristics of this random laser, you can see at the top left there is a photograph of the random laser and the emitted photons without nematicons. So this is green light pumping the cell. Light is emitted upon lasing in this random fashion in the visible, but then it diffracts because there is no waveguide. In the center, you see a photograph of the near-infrared nematicon at 106 microns. This is the near-infrared CW waveguide induced by light. You see it's a non-diffracting self-localized waveguide. And on the right, the combination of a nematicon with random lasing, which provides, of course, guidance to the emitted light. As a result, the photograph shows you the emitted light from the random laser, which is guided and propagates much longer without diffraction because it's guided by the light-induced waveguide. And if you look at the spectra versus wavelength, you see that below threshold, without nematicon, black line, you get a fluorescent spectrum which is broad and irregular. in the presence of a nematicon below threshold, nothing much changes in the red light, in the red curve. But if you go above threshold on the right, you see that you get random lasing in black without nematicon. So it's a very regular and broad spectrum because there are several laser lines in this random system without an external cavity. But when you switch on the nematicon, the spectrum shrinks into the red spectrum simply because the number of modes available for lasing inside a limited volume defined by the waveguide is reduced, and so you get a more coherent spectrum and much narrower than you would without the soliton. So the soliton also increases the coherence of the overall emission and limits the size of the laser spectrum, which is also an improvement as compared to standard random lasing. Now, if you plot the, if you like, the transfer function, so the emitted light versus the pump energy to the laser in the presence or absence of a soliton, you get the black line without a soliton. So this is a standard laser characteristic with an elbow. This is the threshold at about 0.5 microjoules, and then you have the slope defining the amplification of the laser. So the laser works without nematicon, of course, but then when you switch on the nematicon given by the red line, you see that the threshold goes down, so the laser is able to actually lase at a much lower threshold, 0.4 microjoules, and the slope is much higher, so the amplification of the laser is much increased by the presence of this light-induced waveguide. I want to emphasize that this kind of characteristic, and in particular the 2 points alpha and beta indicated in the graph, show you that you can actually make a switch, switching from zero laser emission in alpha in the absence of a nematicon to laser emission for the same pump energy in the presence of a nematicon. So a milliwatt CW beam can switch the laser on and or off, acting upon a pumped system and making the laser work in alpha. Or in beta, you already have a laser at this kind of pump energy, but of course the efficiency and the amplification goes from this value in black to this value in red, so you get a large increase in the emitted light from the laser. So essentially you make an optical transistor which is controlled by a milliwatt power introduced in the near infrared. So this is a transistor in a lasing system. Now if we look at the photograph of the system, these are photographs taken from the output of the cell. What you see on the left is the absence of a nematicon. What you see is the slab of the nematic crystal, and the light is orange because the emitted light from this random laser in filament is around orange, around 180 nanometers. The light above and below the slab is diffracted light and scattered light from the system because the system is a scattering and the light goes out. And you see light fills the cell because there is diffraction in the absence of a waveguide. When I switch on the nematicon, you see on the right, most of the light will be confined by this waveguide. The laser emission gets a transverse profile which is well defined, centered, much more intense, and thereby much more efficient, as shown by this graph at the bottom. You see the efficiency goes up with a variation of milliwatt in power level in the nematicon. Okay, and then finally I'll skip this one. Maybe not. This is walk-off. You have walk-off for the direction of propagation of the soliton depends on the position of the optic axis, but I'm running out of time, so let me skip this. Okay, here. And then, of course, if you look at the nematicon and you launch the nematicon parallel to the floor, so to speak, with your wave vector parallel to Z, the nematicon in a positive uniaxial will walk off with an angle which is about 7 degrees in this material. And so the apparent inclination is due to this walk-off inherent to the system. However, since we are in a cell with nematic crystal and reorientation takes place in the presence of a voltage, we can apply an external voltage and go from this situation. How many minutes? 5 minutes, okay. So I go from this situation in which I have the soliton propagating at an angle with respect to the wave vector because of this uniaxial feature of the system. But if I apply a voltage across the thickness of the cell, then I can reorient the molecules, but the animation doesn't work properly. Okay, let me try again. Okay, so I can reorient the molecules upwards, and thereby I can change the amount of Volkov, and so redirect the Poynting vector of the soliton in the plane. So if I do that and plot the trajectory changing the applied voltage, as in this video, you can see the trajectory changes upon applying a voltage across the thickness. So I'm changing the layout of the uniaxial, and thereby I'm changing the direction of propagation of my soliton. Okay, so I go from 0 to about 2.5 volts, and my soliton goes from 7 degrees to 0 simply by applying an external voltage. And then, of course, I can do the same in my random laser. You see at the bottom left, you see the random laser guided by the Namaticon propagating at 7 degrees in my uniaxial. And then applying a voltage, I can switch from this situation to the situation to the right, in which the Volkov is much reduced because I'm reorienting the molecules and reducing the Volkov. So I go from 0 volt, in which my random laser is emitted in this position, the output of the cell, and then applying 2 volts, my random laser emission switches to this other position, simply because I am reorienting the molecules and the optic axis, so changing theta, if you like, and changing thereby the orientation of the Poynting vector. So this is the first example of a random laser which is controllable in direction by applying a voltage to the active medium. By the same token, I could apply a magnetic field. If I apply a magnetic field, I can also reorient the molecules and the optic axis, and based on the same idea, moving my external magnetic field B from one position to another, I can reorient the molecules. Reorienting the molecules corresponds to changing the layout of the optic axis. Changing the position of the optic axis, I can affect the Volkov. And so by moving my external magnetic field from this position at the top to this other position at the bottom, I reorient the molecules, and I can change the Volkov, so changing the direction of the soliton, and thereby the direction of propagation of the emitted laser light. And so this is a graph, a synopsis of the effects. Here you can change the position of the magnetic field externally applied to the cell, and thereby you change the reorientation, and you still obtain random lasing in different, along different directions with similar spectra, controlling the direction of emission of the system. And this is the result. This time, by changing the position of the magnetic field, you can move the random laser beam from this position to the position swinging over 14 degrees in the output. And of course, this is the first demonstration of a random laser whose direction of emission is controlled by a magnetic field. Finally, and this is my last slide, if I can, otherwise I skip. I can. Okay. And this is a waveguide. Let me remind you, this is about 2 millimeter in propagation, and it's a waveguide induced by light. And so the random laser is guided by light in this ordinary polarization, and so I can control the direction of propagation, I can improve the efficiency, I can control the threshold, etc., etc. And what I showed you was measured at the output of this waveguide, and it's summarized by this photograph on the left column, forward emission. And so you see that by changing the amount of power in the green beam for the soliton, I can go from random lasing to a very nice shape in transverse profile and increase the efficiency and lower the threshold. So apparently this spot is much nicer, and it's definitely much nicer than the spot from a random laser without a waveguide. But what happens backwards, because there is no limitation to emitted photons in direction of propagation. They are also emitted backwards. So if I look at the backward emission, of course I still have a random laser without the benefit of a propagation in a waveguide. And these are the results in this rightmost column. You see that the transverse spot is very poor and remains poor despite the propagation of a nematical, because the waveguide is formed from the beginning on, but not from the beginning back. So going backwards, of course, I lose the benefits of a guided wave propagation. And so the random spots testify the low coherence and the many modes of a random laser. Okay, here I compare, and then in conclusion, I showed you an interesting combination of, an interesting combination of passive and active nonlinear optics in nematic crystals, which are in a way of active materials, but looking for ways to exploit, basic nonlinear optics and special solitons to get a benefit in controlling random lasers and improving the performance of a random laser for potential wealth of application. Here is a summary of what I showed you, and this is the last slide. Thank you very much.